A field is a strange kind of thing, because it can be everywhere without looking like anything at all. It does not need a surface, a colour, or an edge. It can fill a room without rustling the curtains, cross the distance between stars without leaving footprints, and still decide how light behaves, how particles appear, and how matter holds itself together. In modern physics, the universe is not simply a stage filled with objects. It may be more like a quiet web of fields, with the objects themselves appearing as the places where that web begins to ripple. Welcome to the Sleepy Scientist. It's lovely to have you here. Before we settle in, where in the world are you watching from tonight? Maybe you're tucked up in bed, half listening with the lights low. Maybe you're on a quiet evening journey, watching the world slip by outside the window. Or maybe you're curled up somewhere warm, pretending this is definitely not the third video you've put on before sleep. Wherever you are, hopefully you're comfortable, safe, and ready to let your thoughts drift gently into the strange foundations of reality. If you enjoy these slow, relaxing journeys through science and would like more of them, like and subscribe really does help this sleepy little channel keep floating along. And if you're already subscribed, thank you. Truly. Your support makes all the difference, and it's very much appreciated. Now, tonight's topic does come with a small warning. It may make the room around you feel slightly less ordinary than it did a few minutes ago, but with any luck, not in a stressful way. More in the gentle, mildly suspicious way one might look at a table after learning it is mostly quantum structure pretending very convincingly to be furniture. So let's begin, shall we? Do quantum fields create reality? And if they do, what does that mean for the solid, glowing, strangely reliable universe quietly surrounding you right now? The world feels firm long before it feels mysterious. A table holds a cup without complaint. A wall stays politely in place. The floor does not seem to be negotiating with the laws of nature before deciding whether to support your feet. Everything appears to be made of objects with surfaces, edges, weights, textures, and positions. Matter feels like stuff. Space feels like the gap between stuff. Light seems to move through that space, bouncing from one surface to another, letting the eyes build a picture of a world that is solid, separate, and reassuringly familiar. This everyday picture is not wrong. It works beautifully at the scale of hands, houses, chairs, mountains, and mugs of tea that have been forgotten just long enough to become disappointing. The ordinary world is real. Its solidity is real. The warmth of a lamp, the pressure of a pillow, the quiet resistance of a closed door, all of these are genuine experiences produced by genuine physical processes. But modern physics suggests that this familiar layer is not the deepest layer. Beneath the surfaces and shapes, the universe appears to be built from something stranger, quieter, and far less intuitive. At the deepest level currently described by physics, particles are not usually treated as tiny hard grains of matter, like miniature stones scattered through empty space. In quantum field theory, particles are understood as excitations of fields. An electron is not simply a little bead with electric charge. It is detectable excitation of the electron field. A photon, the quantum of light, is an excitation of the electromagnetic field. Quarks, which help make up protons and neutrons, are excitations of quark fields. The Higgs boson is an excitation of the Higgs field. Reality in this view is not only populated by fields, it is deeply shaped by them. This brings us to the central question: do quantum fields create reality? The careful answer begins by removing a possible misunderstanding. This does not mean that thoughts, wishes, dreams, or consciousness magically invent the universe. Quantum fields are not a mystical permission slip for pretending that a parking fine disappears if ignored with enough confidence. They are physical concepts within a mathematical theory, tested through experiments and used to describe real particles, forces, and interactions. When physicists say that particles arise from fields, they are not saying reality is imaginary. They are saying that what seems like a collection of tiny separate things may be the visible behavior of deeper field structures. So, in a scientific sense, quantum fields may be among the ingredients from which the experienced world emerges. They help explain why matter exists in familiar forms, why light comes in quantum packets, why atoms can be stable, why forces act between particles, and why empty space is not quite the blank nothingness it appears to be. They do not create reality like an artist painting a picture from outside the universe. They are more like part of the universe's own hidden grammar, the quiet rules and structures that allow the picture to exist at all. There is an important distinction here between everyday reality and physical reality. Everyday reality is the level of chairs, skin, glass, water, breath, clouds, phones, floors, and stars in the night sky. It is the reality the senses evolved to handle. It is practical, stable, and usually kind enough not to reveal quantum field theory while someone is trying to find their slippers. Physical reality, as described by fundamental physics, is more abstract. It speaks in terms of fields, energy, symmetries, interactions, quantum states, measurements, and conservation laws. These ideas are not less real because they are harder to picture. They are often more precise than the images the mind uses to make the world feel simple. Quantum field theory is one of the most successful frameworks ever developed in science. It underlies particle physics, quantum electrodynamics, parts of nuclear physics, and the Standard Model of particle physics, which describes known fundamental particles and 3 of the 4 fundamental interactions. It has helped predict and explain phenomena with astonishing accuracy, especially in the case of quantum electrodynamics, the theory describing how light and charged particles interact. It is not a vague philosophical suggestion. It is a working scientific structure, one that has survived some of the most demanding tests human beings have managed to design. And yet, it remains quietly strange. If particles are field excitations, then the universe is not quite the simple theatre of objects it first appears to be. A solid table is not solid because its atoms are packed like tiny marbles, with no space between them. It feels solid because electrons, atomic nuclei, electromagnetic forces, quantum rules, and the Pauli exclusion principle combine into a stable pattern. Your hand does not pass through the table, because the underlying fields and interactions do not allow that arrangement to unfold in the easy way everyday language might imagine. Matter is not hardness all the way down. It is structure, relationship, resistance, and energy, organized by rules far beneath sensation. This is why the familiar world can be both ordinary and deeply surprising. A room can be quiet, dim, and peaceful, while also being filled with electromagnetic fields, electron fields, quark fields, and the subtle activity of quantum systems. The air can seem empty while containing molecules made from atoms shaped by quantum mechanics, and particles described by fields extending through space-time. Light can look like a gentle glow on a wall, while also being an excitation of a field that connects electricity, magnetism, relativity, and quantum theory. The deeper machinery stays hidden because human senses are built for survival, not for detecting the architecture of fundamental physics. Eyes notice surfaces, not wave functions. Hands feel pressure, not field excitations. Ears hear vibrations in air, not the quantum description of the atoms carrying them. The brain turns the world into a usable story, and most of the time that story is exactly what is needed. But beneath that story is another one. It is quieter, stranger, and more precise. The solid world may be the surface of a deeper field-based reality, where particles are not the beginning of the explanation, but the things that appear when fields behave in particular ways. And if that is true, then quantum fields do not make reality less real. They make reality more mysterious, more structured, and far more elegant than it first appears. For a long time, reality seemed easiest to imagine as matter moving through emptiness. The world appeared to be made from solid pieces, some large enough to hold in the hand, some so small they had to be guessed rather than seen. Stones, planets, raindrops, iron tools, grains of sand, and human bodies could all be pictured as collections of material parts arranged in different ways. Space, meanwhile, seemed like the silent gap between them, a kind of invisible room where matter could travel, collide, rest, spin, fall, and gather. This older picture was not foolish. It was powerful, practical, and often beautifully accurate. It helped people describe falling apples, swinging pendulums, cannonballs, tides, moons, and planets. It turned the motion of the heavens from something mysterious and symbolic into something that could be measured. If reality was made of stuff, then perhaps understanding reality meant understanding how pieces of stuff pushed, pulled, and moved. Isaac Newton gave this view one of its greatest forms. In the late 17th century, Newton's laws of motion and universal gravitation described a universe where objects followed clear mathematical rules. A body at rest remained at rest unless acted on by a force. A body in motion continued in motion unless something changed it. Force, mass, and acceleration were tied together in a way that allowed motion to be predicted with extraordinary success. Gravity, in Newton's theory, pulled every mass toward every other mass, from a falling apple near Earth to the moon circling above it. Newton's physics was a masterpiece. It remains useful today for bridges, vehicles, sports, engineering, astronomy, and the everyday motions of ordinary things. If a cup slides off a table, quantum field theory is not usually required to explain the sad little ceremony that follows. Newton does the job perfectly well, right up to the part where someone has to clean the floor. His work showed that nature could be described by laws rather than by guesswork, and it gave science a confidence that the universe was understandable. But Newton's picture also left deep questions behind. Gravity acted across empty space, but how did one object know another was there? How could the sun influence Earth across such an enormous distance without anything visibly connecting them? Newton himself was cautious about claiming to know the mechanism behind gravity. His equations described what gravity did with stunning precision, but the deeper question of how influence travelled through space remained unsettled. This is where the idea of a field began to change the imagination of physics. A field is a way of describing something that has a value throughout space. Instead of thinking only about isolated objects and direct contact, physicists began to imagine space itself as carrying physical influence. A magnetic field around a magnet, for example, is not seen directly in the way a stone is seen, but its presence can be revealed by iron filings, compass needles, or the motion of charged particles. The invisible becomes visible through what it makes happen. Michael Faraday was one of the great figures in this shift. In the 19th century, Faraday studied electricity and magnetism with remarkable experimental skill. He pictured electric and magnetic effects using lines of force, invisible patterns stretching through space around charged objects, magnets, and electric currents. To Faraday, these lines were not merely a convenient drawing. They suggested that space around objects was physically structured. Something real was present there, even when no solid material could be touched. This was a profound change. Reality no longer had to be imagined only as lumps of matter separated by emptiness. The region between objects could have properties of its own. A magnet did not need to touch a piece of iron to influence it. An electric charge did not need a little mechanical arm reaching across space. The field carried the possibility of action. It gave physics a new way to describe influence as something spread out, continuous, and present even where matter seemed absent. James Clerk Maxwell then gave Faraday's vision a powerful mathematical form. Maxwell showed that electricity and magnetism were not separate curiosities, but two linked aspects of one electromagnetic field. Changing electric fields could produce magnetic fields, and changing magnetic fields could produce electric fields. This relationship allowed disturbances in the electromagnetic field to travel as waves. The most astonishing result was that these waves moved at the speed of light. Maxwell realized that light itself was an electromagnetic wave. A candle flame, a sunbeam, the glow of a distant star, and the colors passing through a prism were all expressions of the same underlying electromagnetic reality. Light was no longer just something that helped the eye see objects. It was a field phenomenon, a traveling ripple in electricity and magnetism. This changed the meaning of empty space. Space was not simply a blank container waiting for matter to pass through it. It could carry electromagnetic waves across enormous distances. It could hold electric and magnetic fields. It could transmit sunlight from the sun to Earth in about 8 minutes, crossing roughly 150 million kilometers without needing air, water, glass, or any ordinary material support. That fact alone is quietly astonishing. The warmth on a face during the day arrives because fields can carry energy through what appears to be emptiness. By the end of the 19th century, physics had already moved far beyond the simple idea of solid stuff in passive space. Newton's mechanical universe was still powerful, but Faraday and Maxwell had revealed another layer. Fields could be real. Invisible structure could fill space. Influence did not always need direct contact between material objects. Quantum theory had not yet arrived, but one of its most important ingredients was already waiting. Before particles became excitations of quantum fields, fields first had to be accepted as part of reality at all. The universe was beginning to look less like a collection of isolated pieces moving through nothing, and more like a continuous physical presence, spread through space, shaping what matter does, how light travels, and how reality quietly holds itself together. By the late 19th century, physics had become almost dangerously confident. Not arrogant exactly, but perhaps leaning back in its chair a little too comfortably. Newton's mechanics described the movement of ordinary objects with extraordinary success. Maxwell's electromagnetism had united electricity, magnetism, and light into one elegant theory. Thermodynamics explained heat, engines, energy flow, and the strange one-way drift of processes toward disorder. Chemistry was becoming increasingly precise, with atoms and molecules helping explain why substances reacted, combined, burned, dissolved, and sometimes made alarming smells in laboratories. Taken together, these ideas formed an impressive picture of nature. Matter moved according to mechanical laws. Light travelled as an electromagnetic wave. Heat could be understood through energy and the motion of particles. Chemical behaviour could be organised through atoms, bonds, and elements. It was tempting to imagine that the deepest foundations were nearly complete, and that future physicists would mostly polish the details, tidy the edges, and perhaps invent better ways to stop chalk dust getting everywhere. But nature had kept a few small cracks hidden in the walls. One of those cracks involved black-body radiation. A black-body is an ideal object that absorbs and emits radiation according to its temperature. In practical terms, it helped physicists understand why hot things glow, first red, then orange, then white, as the temperature rises. Classical physics could describe part of this pattern, but when it tried to predict the full spectrum of radiation, especially at shorter wavelengths, it failed badly. The calculation suggested an impossible runaway of energy. This problem became known as the ultraviolet catastrophe, which is a dramatic name, but in fairness, physics had briefly predicted something catastrophically wrong, so the name earned its little cape. In 1900, Max Planck found a way through the problem. He proposed that energy was not exchanged in a perfectly smooth, continuous flow. Instead, the energy of radiation seemed to be emitted or absorbed in discrete amounts. These small packets of energy were called quanta. Planck did not initially present this as a grand new picture of reality. It was, at first, a mathematical solution to a stubborn problem, but it opened a door that classical physics could not close again. Energy, at least in this context, behaved as though nature kept count. Another crack appeared in the photoelectric effect. When light shines on certain metals, electrons can be knocked out from the surface. Classical wave theory suggested that brighter light should provide more energy, gradually building up until electrons escaped. But experiments showed something stranger. Below a certain frequency, no electrons were emitted, no matter how intense the light was. Above that frequency, electrons could be emitted even when the light was weak. In 1905, Albert Einstein explained this by treating light as if it arrived in packets of energy. These packets would later be called photons. The energy of each packet depended on the light's frequency. A single photon of high enough energy could knock an electron free, while many lower energy photons could fail to do so. Light, which Maxwell had described so beautifully as a wave, now seemed to behave like a collection of discrete units. It was not simply wave or particle. It was something deeper, refusing to fit neatly into either familiar box. Atoms created another problem. Classical electromagnetism said that accelerating electric charges should radiate energy. An electron orbiting an atomic nucleus should therefore lose energy and spiral inward. If that were true, atoms should collapse almost immediately. Matter would not be stable. Tables, stars, people, oceans, and biscuits would all be in serious structural trouble, which is inconvenient for physics and terrible for tea. Niels Bohr offered an early quantum model of the atom in 1913. In his model, electrons could occupy only certain allowed energy levels around the nucleus. They didn't radiate energy while remaining in these permitted states. They could absorb or emit energy only when jumping between levels. This helped explain atomic spectra, the specific line of color produced when atoms emit or absorb light. Each element had its own pattern, like a fingerprint written in light. Bohr's model was not the final theory of atoms, but it revealed something essential. The inner world of matter was not obeying classical expectations. Energy levels were discrete. Light could behave as packets. Matter remained stable because quantum rules prevented the collapse that older theories predicted. The universe was not merely a smooth machine made of tiny parts. It was using rules that seemed both wave-like and particle-like, continuous in some ways, counted in others. These cracks in classical reality were not failures in the ordinary sense, they were clues. Newton, Maxwell, thermodynamics, and chemistry had not been thrown away. They remained astonishingly useful, especially at human scales. But they were no longer enough to describe the deepest behavior of matter and light. The path toward quantum fields began here, with the discovery that reality could not be explained only by smooth waves or tiny solid particles. Nature seemed to speak both languages while belonging fully to neither. Energy came in quanta. Light spread like a wave but arrived like a packet. Atoms were stable because hidden quantum rules shaped their possibilities. The solid world had not disappeared, but beneath it the old classical floorboards had begun to creak. The strange thing about quantum physics is that it did not merely make particles smaller, faster, or harder to observe. It made them harder to describe in ordinary language at all. Classical physics had offered two familiar categories. A particle was a little object with a position, a path, and a definite motion. A wave was something spread out, like a ripple on water or a vibration in air. These two ideas felt different enough to keep politely apart. Then quantum theory arrived, and nature began placing them in the same room without asking anyone's permission. Light had already caused trouble by behaving like both a wave and a packet of energy. But soon the problem moved in the opposite direction. If light, once thought of as a wave, could behave like particles, could matter, once thought of as particles, behave like waves? In 1924, Louis de Broglie proposed exactly that. He suggested that matter has wave-like properties, meaning that electrons and other particles are associated with wavelengths. This was a bold idea. An electron had been imagined as a tiny charged particle, something much more like a speck than a ripple. De Broglie's proposal said that the electron was not simply a miniature billiard ball, quietly rolling around the atomic table. It had a wave character as well. Not a wave made of water or air, but a quantum wave connected to the probability and behavior of matter. This idea was soon supported by experiments. Electrons could produce diffraction patterns, which are usually associated with waves. When waves pass through narrow openings or around edges, they spread and interfere. Bright and dark bands can appear where wave crests reinforce or cancel each other. To see electrons do something similar was deeply unsettling in the best scientific way. Matter, which had seemed so satisfyingly chunky, was now acting as though it could spread out, overlap, and interfere with itself. The double-slit experiment remains one of the clearest windows into this strangeness. When particles such as electrons are sent toward a barrier with two narrow openings, and then detected on a screen beyond, they can build up an interference pattern over time. This happens even when electrons are sent one at a time. Each electron is detected as a single event, a little spot on the screen, but the total pattern looks wave-like. It is as though each individual quantum object travels according to possibilities that pass through both openings, while the final detection appears as one definite result. This does not mean an electron is secretly a tiny marble that knows a clever shortcut. It also does not mean it is simply an ordinary wave spread through space in the same way as sound. Quantum objects resist both pictures. They arrive in discrete detections, but their behavior before detection is described by wave-like mathematics. The word particle still helps in some situations, and the word wave helps in others, but neither word fully captures what is happening. Everyday language begins to run out of furniture. Erwin Schrödinger developed wave mechanics in 1926, giving physicists a way to describe quantum systems through wave functions. The wave function does not describe a physical water-like ripple. It encodes information about the possible outcomes of measurements, such as where a particle may be detected. At almost the same time, Werner Heisenberg developed matrix mechanics, a different mathematical approach that focused on observable quantities rather than picturable paths. These two theories looked very different at first, but they were soon shown to be equivalent descriptions of the same quantum reality. Heisenberg also introduced the uncertainty principle, one of the most famous and most misunderstood ideas in physics. It does not simply say that instruments are clumsy, or that measuring tiny things is difficult because the equipment keeps bumping into them. The uncertainty principle says that certain pairs of properties, such as position and momentum, cannot both have perfectly definite values at the same time in the quantum description. This is a feature of how quantum systems are structured, not merely a practical inconvenience. Nature is not hiding sharp classical answers behind a curtain, while physicists use the wrong torch. The wave-particle problem became one of the essential bridges toward quantum field theory. It showed that particles could not be understood as basic little lumps with simple paths through empty space. Their behavior was more spread out, more abstract, and more deeply tied to probability than classical physics had allowed. The old categories had been useful, but they were not fundamental enough. Quantum fields would later offer a broader way to think about this. Instead of asking whether an electron is truly a wave or truly a particle, physics could describe it as an excitation of an underlying field. The particle-like detection and the wave-like behavior would become different aspects of a deeper framework. Reality was beginning to look less like a universe made from tiny things moving through nothing, and more like a universe where what seems like a thing is often the visible trace of something far more subtle. Early quantum mechanics was a triumph, but it was not the end of the story. It explained atomic structure with a depth classical physics had never managed. It gave physicists a way to understand why atoms emit and absorb specific colors of light, why electrons occupy allowed states, why matter does not simply collapse, and why tiny systems behave according to probability rather than neat mechanical paths. For atoms moving slowly compared with light, it worked with remarkable success. The microscopic world had become strange, but it had also become measurable. Yet there was another great idea waiting at the door, quietly refusing to be ignored. In 1905, Albert Einstein introduced special relativity, and it changed the meaning of space, time, motion, energy, and mass. Special relativity begins with two central principles. The laws of physics are the same for observers moving at constant velocity relative to one another, and the speed of light in a vacuum is the same for all such observers. That second idea sounds simple until it starts rearranging reality's furniture. If the speed of light is fixed in this way, then time and space cannot be absolute in the old Newtonian sense. Moving clocks tick differently compared with stationary ones. Lengths along the direction of motion are measured differently. Events that seem simultaneous to one observer may not be simultaneous to another. Space and time are woven together into space-time, a single framework in which motion, measurement, and causality are linked. The universe was no longer a stage with one universal clock mounted neatly on the wall. Special relativity also revealed a deep connection between energy and mass. The famous idea is usually written as a short equation, but for voiceover it can be read as energy equals mass multiplied by the speed of light squared. This means mass can be understood as a concentrated form of energy, and energy can contribute to mass. The connection is not a poetic metaphor. It is part of the working machinery of nuclear physics, particle physics, stars, and high-energy processes across the universe. This mattered because early quantum mechanics did not fully include relativity. Schrödinger's wave mechanics was extremely powerful for many atomic situations, but it was not built for particles moving close to the speed of light. It also usually dealt with a fixed number of particles. One electron remained one electron. Two particles remained two particles. That is often perfectly useful for atoms, molecules, and many low-energy systems, but nature is not always so tidy. In high-energy interactions, particles can be created and destroyed. A photon with enough energy can produce matter and antimatter under the right conditions. An unstable particle can decay into other particles. In particle accelerators, energy can be transformed into new particle excitations that did not exist in the initial state. Cosmic rays striking Earth's atmosphere can produce showers of secondary particles. Stars, supernovae, black holes, and the early universe all involve conditions where particle number is not a sacred little accounting rule. A deeper theory had to respect both quantum behavior and special relativity. It had to allow uncertainty, wave-like probability, discrete measurement outcomes, and the fixed speed limit of light. It also had to cope with the fact that particles are not always permanent little beads travelling through space with lifelong identity cards. Paul Dirac made a major step in this direction in 1928. He developed the Dirac equation, a relativistic quantum equation for the electron. It combined quantum mechanics with special relativity in a new and powerful way. But it also brought something unexpected. The mathematics seemed to imply the existence of a counterpart to the electron, with the same mass and opposite electric charge. This was not just a mathematical nuisance to be swept discreetly under the theoretical carpet. It pointed toward antimatter. In 1932, Carl Anderson observed the positron, the electron's antimatter partner, in cosmic ray experiments. Dirac's theory had led physics to a real particle that had not previously been known. This was an extraordinary moment. Trying to make quantum theory compatible with relativity had revealed that reality contained more possibilities than ordinary matter alone. But it also showed that the older particle picture was becoming strained. If particles can appear and disappear, then perhaps particles are not the most basic things. Perhaps the deeper entities are fields, and particles are the excitations that those fields produce when energy is arranged in particular ways. This is why ordinary quantum mechanics was not enough. It had opened the door to the microscopic world, but quantum field theory was needed to walk further in. Reality did not preserve little particle identities as neatly as everyday imagination preferred. It behaved more like a field-based system, where what appears as matter can emerge, transform, vanish, and return according to deeper rules. Quantum field theory begins with a strange but powerful shift in perspective. Instead of treating particles as the deepest building blocks of nature, it treats fields as the deeper layer. A field is something that has a value or a set of values throughout space and time. In classical physics, the electromagnetic field could already stretch across empty space and carry light. In quantum field theory, fields become quantum objects. They obey quantum rules. They can gain energy in discrete amounts, and those discrete amounts are what are detected as particles. This is one of the most important ideas in modern physics. In quantum field theory, an electron is not best imagined as a tiny hard speck that simply exists on its own. It is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Quarks are excitations of quark fields. Gluons are excitations of the gluon field. The Higgs boson is an excitation of the Higgs field. The known universe, at its most fundamental tested level, begins to look less like a box of little objects and more like a collection of fields whose activity can appear as particles. This does not mean the universe is made from a substance like water, air, fog, or some cosmic jelly. It is tempting to imagine fields as if they were an invisible fluid filling everything, but that picture can mislead as much as it helps. A quantum field is not a material ocean sloshing around behind reality. It is a physical entity described by values and rules across space-time. It can carry energy and momentum. It can interact with other fields. It can be measured through the particles and effects it produces. But it does not need to be made of ordinary stuff, because ordinary stuff is partly what it is trying to explain. Particles, in this picture, are stable and measurable excitations of fields. A useful image is a ripple, but only if the image is handled gently. A ripple on a pond is made from water moving up and down. A particle is not a little bump in a hidden liquid. It is more abstract than that. It is a quantum excitation with definite properties such as mass, electric charge, spin, and energy. When a detector records a particle, it is detecting one of these field excitations through its interaction with other physical systems. The click in a detector, the mark in a chamber, or the signal in a particle experiment is the observable trace of field behavior. This idea helps explain something ordinary particle language struggles with. In the world of high-energy physics, particles can appear and disappear. They can be created in collisions and destroyed in interactions. An unstable particle can decay into other particles. A photon can be absorbed by an atom. A particle and its antiparticle can annihilate, transforming their energy into other field excitations. This would be very odd if particles were permanent little marbles. Marbles do not usually vanish into flashes of energy unless someone has designed an exceptionally worrying toy box. Quantum field theory handles this naturally. It includes mathematical tools known as creation and annihilation operators. The names sound dramatic, as though physics has wandered into a fantasy novel with better notation, but the idea is precise. These operators describe how the number of field excitations can change. A field can gain an excitation, which is observed as the creation of a particle. A field can lose an excitation, which is observed as the removal or absorption of a particle. The deeper field remains, while its detectable excitations can come and go. This is why quantum field theory became so important after early quantum mechanics. Ordinary quantum mechanics could describe many systems where the number of particles stayed fixed. Quantum field theory could describe a world where energy, relativity, and quantum behavior all work together, and where particle number can change. It gave physics a framework for particle accelerators, radioactive decay, electromagnetic interactions, nuclear forces, and the standard model of particle physics. Here, the title begins to take on its first careful meaning. Do quantum fields create reality? Not in the sense of imagination creating the world, and not in the sense of a field sitting outside the universe making things by choice. But in a scientific sense, quantum fields provide the underlying structures whose excitations are detected as matter and radiation. The electron field helps give rise to electrons. The electromagnetic field gives rise to photons. Quark and gluon fields help form protons, neutrons, and the nuclei inside atoms. The solid world is still real. Light is still real. Matter is still real. But the deeper description has changed. What looks like a universe made first of particles may be a universe made first of fields, with particles appearing as the moments when those fields become measurable in particular ways. Reality begins to look less like a pile of tiny things and more like an ongoing pattern of fields, interactions and excitations, quietly producing the matter and light that make the world visible. The electron field is one of the quiet reasons the familiar world feels familiar at all. It is not the only field involved in reality, but it is one of the most important for ordinary experience. Without electrons, there would be no chemistry in the form known on Earth, no ordinary electricity, no glowing screens, no stable atoms arranged into bodies, books, oceans, leaves, blankets, or cups of tea sitting bravely beside complicated physics. The electron may seem tiny, but its field has an enormous influence on the shape and behavior of everyday life. In quantum field theory, every electron is understood as an excitation of the same underlying electron field. This is a subtle but important idea. Electrons are not little objects manufactured separately in different parts of the universe, each with its own private identity and tiny suitcase. They are excitations of one field that exists throughout space-time. An electron in a copper wire, an electron in an atom of oxygen, and an electron in a distant star are all examples of the same kind of field excitation. They have the same electric charge, the same mass, and the same spin because they arise from the same underlying field. This is one reason electrons are so perfectly alike. In everyday life, two pebbles are never truly identical. One has a slightly different shape, a faint crack, a little scratch, a history of where it has been. But electrons are not like pebbles. As far as physics can measure, one electron is indistinguishable from another. The electron field gives rise to excitations with the same fundamental properties wherever they appear. This sameness is not a boring detail. It is part of why atoms behave consistently, why chemistry can be reliable, and why the universe does not have to keep inventing new rules for every molecule, which would be extremely creative but deeply inconvenient. Electrons help determine the structure of atoms. Around each atomic nucleus, electrons occupy quantum states, often described in terms of orbitals. These are not little circular tracks like planets around a star. They are probability patterns shaped by quantum mechanics that describe where electrons are likely to be found and what energies they can have. The arrangement of electrons around nuclei largely determines how atoms interact with one another. It explains why oxygen behaves differently from carbon, why sodium reacts eagerly with chlorine, and why gold sits around being impressively unreactive and shiny. Chemical bonding depends heavily on electron behavior. Atoms form bonds by sharing, transferring, or redistributing electrons. Covalent bonds, ionic bonds, metallic bonds, and the weaker interactions between molecules all rely on electromagnetic attraction and quantum rules involving electrons. The shapes of molecules from water to DNA depend on how electrons arrange themselves around atomic nuclei. These shapes matter enormously. A molecule's shape can affect how it reacts, how it dissolves, how it fits into enzymes, how it carries information, and whether it smells like vanilla or like something that should be removed from the fridge with caution. Electrons also make electricity possible. In metals such as copper, some electrons can move through the material more freely than others. Their collective behavior allows electric current to flow. This is the basis of wires, circuits, motors, computers, lights, and much of modern technology. Electron behavior also helps explain conductivity, insulation, semiconductors, and superconductivity. A conductor allows charge to move easily. An insulator keeps electrons more tightly bound. A semiconductor sits in a useful middle ground, which is why silicon became so important for electronics. Much of the digital world rests on the controlled movement of excitations of the electron field. Magnetism, too, is connected to electrons. Electrons have a quantum property called spin, along with electric charge, and both contribute to magnetic behavior. In some materials, many electron spins can align in a coordinated way, producing ferromagnetism, the kind seen in familiar permanent magnets. In other materials, electron arrangements lead to weaker or more temporary magnetic effects. The magnetic field around a fridge magnet may seem like a simple household trick, but beneath it lies quantum behavior arranged across countless atoms. Even the humble magnet has hidden depths, which is a polite way of saying the fridge has been showing off quietly for years. One of the most important ideas for understanding matter's structure is the Pauli exclusion principle, introduced by Wolfgang Pauli. This principle says that identical fermions, such as electrons, cannot occupy the same quantum state at the same time. It is a defining rule of electron behavior. Without it, electrons in atoms would not arrange themselves into shells and orbitals in the same way. They would crowd into the lowest available state, and matter would lose the layered structure that makes chemistry possible. The periodic table, with all its patterns and personalities, depends deeply on this principle. The Pauli exclusion principle also helps explain why matter takes up space. Ordinary objects feel solid not because atoms are tiny hard balls pressed edge to edge with no room between them. Atoms are mostly empty space by volume, if imagined in simple classical terms. Yet a hand does not pass through a table, because electron fields, electromagnetic repulsion, and quantum rules prevent the atoms in the hand and the atoms in the table from simply overlapping into the same states. Solidity is not microscopic hardness, it is organized resistance. So when the world feels firm beneath your fingertips, the electron field is part of that sensation. When light reflects from a surface, electrons in atoms are involved. When nerves carry signals, when muscles move, when molecules fold, when metals conduct, when magnets cling, and when chemistry builds living cells, the electron field is quietly present in the explanation. It does not create reality alone, but it helps give reality much of its texture, stability, variety, and touchable form. A single field spread through space-time contributes to the feeling that the world is solid, colourful, responsive, and real. Light is one of the gentlest things in daily experience, and one of the most revealing. It slips through windows, warms skin, glitters on water, reflects from faces, carries colours into the eye, and travels from stars that may have burned for millions or billions of years before their photons arrived here. It feels almost weightless in thought, like something halfway between substance and message. Yet in modern physics, light is not merely brightness moving through space. It is a quantum expression of the electromagnetic field. The photon field is the quantum field associated with electromagnetic radiation. This includes visible light, but visible light is only a small part of a much wider family. Radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays and gamma rays are all forms of electromagnetic radiation. They differ mainly in wavelength, frequency, and energy. A radio wave crossing a city, the warmth felt from infrared radiation, the ultraviolet light that can redden skin, and the X-rays used to see inside the body all belong to the same deep physical category. They are different notes played by the electromagnetic field. In classical physics, James Clerk Maxwell showed that electricity and magnetism are joined together. A changing electric field can produce a magnetic field, and a changing magnetic field can produce an electric field. Together, they can travel through space as electromagnetic waves. This was one of the great unifications in physics, because it revealed that light itself is an electromagnetic wave. A beam of sunlight and a changing electric current were no longer separate mysteries. They were part of one field-based description of nature. Quantum theory added another layer. In quantum electrodynamics, the electromagnetic field is quantized. Its energy is not exchanged in any amount whatsoever, but in discrete excitations called photons. A photon is not a tiny glowing pellet in the everyday sense, although that image is sometimes tempting. It is a quantum excitation of the electromagnetic field. When an atom emits light, it can release energy as a photon. When an atom absorbs light, it can take in a photon's energy and move into a different energy state. What appears as a beam, a glow, or a flash is built from these quantum exchanges. This is why light can seem wave-like and particle-like depending on how it is measured. It spreads, diffracts, and interferes like a wave, but it is detected in discrete events. A sensitive detector does not receive half a smear of light in the way a water tank receives a ripple. It records individual interactions, one photon at a time. Over many events, wave-like patterns appear. The electromagnetic field provides the deeper structure that makes both descriptions useful, without forcing nature to squeeze itself into either everyday category. Light allows reality to be seen. It reflects from surfaces into the eye, where photoreceptor cells in the retina respond to incoming photons. It lets a camera collect images, a telescope study galaxies, and a microscope reveal structures too small for unaided sight. Light also allows reality to be measured. Astronomers study starlight to learn the chemical composition, temperature, motion, and distance of stars and galaxies. The cosmic microwave background, a faint afterglow from the early universe, carries information from when the cosmos became transparent hundreds of thousands of years after the Big Bang. In a very real sense, much of what is known about the universe arrives as light. Light warms as well as reveals. Sunlight carries energy to Earth across roughly 150 million kilometers of space, helping drive weather, climate, photosynthesis, and much of the living world's energy flow. Electromagnetic radiation also carries signals. Radio broadcasts, wireless internet, satellite communication, radar, remote controls, and fiber optic cables all rely on controlled electromagnetic behavior. The modern world is not just lit by photons, it quietly talks using them. Quantum electrodynamics, often called QED, is the quantum field theory describing how light and charged particles interact. Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga played central roles in developing it, and their work helped create one of the most precise theories in all of science. Its predictions agree with experiments to an extraordinary degree, especially in measurements involving the electron's magnetic properties. That level of precision is not just impressive, it is almost rude. A theory has very little business being that accurate and still leaving reality feeling mysterious. Electromagnetic interactions are central to ordinary matter. They shape atoms, chemical bonds, biological molecules, electricity, magnetism, touch, friction, color, and vision. Almost every familiar experience of matter depends on charged particles interacting through the electromagnetic field. The photon field, therefore, does not simply provide light as a decorative extra. It helps govern how matter behaves and how matter becomes visible. So quantum fields do not only help build the substance of the world, they also make possible the light by which the world is revealed. The same field that carries starlight across the dark also helps atoms exchange energy, lets eyes receive images, and allows distant galaxies to become knowable. Reality is not merely made of things sitting in space, it is also made of signals, interactions, and illumination. And in the quiet language of modern physics, light is the electromagnetic field speaking in quanta. At the centre of ordinary matter beneath chemistry, light, touch, and the electron arrangements that give atoms their shape, there is another layer of fields. Protons and neutrons sit inside atomic nuclei, and for a long time it was natural to picture them as tiny solid balls. They had mass, they took up a place in the atom, and they helped form the heavy centre around which electrons were arranged. But the deeper story turned out to be less like a box of little marbles, and more like a storm so tightly bound that it behaves as a stable particle. Protons and neutrons are composite particles. They are made from quarks, bound together by the strong nuclear interaction. In quantum field theory, quarks are excitations of quark fields. There are several kinds of quarks, known as flavors, including up quarks and down quarks, which are the most important for ordinary matter. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. That simple description is useful, but it is only the beginning, because the inside of a proton or neutron is not a quiet little arrangement of 3 beads. It is a dynamic quantum system filled with quarks, antiquarks, gluons, and field energy. The quark model was developed in the 1960s, with Murray Gell-Mann and George Zweig independently proposing that particles such as protons and neutrons could be understood as combinations of more fundamental constituents. Gell-Mann gave these constituents the name quarks. At first, quarks were partly a way to make sense of the growing zoo of particles being discovered in experiments. Physics had begun to look as if nature had spilled an entire drawer of particle names across the floor. The quark model brought order, showing that many particles could be grouped and understood through deeper patterns. The theory that describes the strong interaction is called quantum chromodynamics, often spoken as QCD. It is the quantum field theory of quarks and gluons. Quarks carry a property called color charge, although this has nothing to do with ordinary color. It is not red like a rose or blue like the evening sky. It is a name for a type of charge involved in the strong interaction. Gluons are the field excitations that carry the strong force between quarks. Unlike photons in electromagnetism, gluons also carry the kind of charge they respond to, which makes the strong interaction especially rich and complicated. One of the strangest features of quantum chromodynamics is confinement. Quarks are not found freely on their own under ordinary conditions. If energy is used to try to pull quarks apart, the strong field does not simply weaken in the familiar way gravity or electromagnetism does over distance. Instead, the energy in the field can become large enough to produce new particles. It is a little as if nature refuses to let anyone take a single quark home in a pocket. Quarks remain confined inside composite particles such as protons, neutrons, and other hadrons. Another key feature is asymptotic freedom. David Gross, Frank Wilczek, and David Politzer showed that quarks interact more weakly when they are extremely close together, or when probed at very high energies. At very short distances, quarks behave more almost free inside protons and neutrons. At larger distances, the strong interaction becomes stronger, leading to confinement. This is one of those beautifully counterintuitive pieces of physics where nature behaves almost opposite to everyday expectation, as though it read the instruction manual and then quietly improved it. The strong interaction also changes how mass should be understood. The bare masses of the quarks inside protons and neutrons account for only a small fraction of the mass of ordinary matter. Most of the mass of a proton or neutron comes from the energy of the strong interaction, including the motion of quarks and the energy stored in gluon fields. Since mass and energy are deeply connected, the mass of the visible matter around us is largely field energy held in stable form. This means the weight of the world is not simply the weight of little solid parts. It is the weight of field dynamics, binding energy, motion, confinement, and quantum structure. The mass in a hand, a stone, an ocean, or a planet comes mostly from protons and neutrons, and much of their mass comes from the restless strong interaction inside them. So quantum fields do not merely decorate matter after it already exists. They help give matter its mass, its stability, and its internal structure. The visible world is heavy not just because particles are present, but because fields are active within those particles, binding quarks together and storing energy in a form that becomes the substance of atoms. Reality, once again, is not made from stillness at the bottom. It is made from organized activity, held so tightly and consistently that it feels solid. The strong nuclear force is one of the quiet reasons atoms can be more than lonely hydrogen. It works at distances so tiny that ordinary imagination has very little to hold on to, yet its effects are everywhere. It helps bind quarks inside protons and neutrons, and it also helps atomic nuclei remain together despite the electric repulsion between positively charged protons. Without it, the universe would not have the same kind of atoms, the same kind of chemistry, or the same kind of stable matter. Reality would not merely look different. It would lose much of the structure that allows rocks, oceans, stars, planets, and bodies to exist at all. Inside protons and neutrons, the strong interaction is carried by gluons. A gluon is the field excitation associated with the strong force, just as a photon is associated with the electromagnetic field. But this image needs care. It is sometimes said that particles exchange force-carrying particles as if tiny messengers were being thrown back and forth across microscopic space. That picture can be useful as a first step, But quantum field theory is deeper than a game of subatomic catch. The strong interaction is described by quark fields and gluon fields interacting according to the rules of quantum chromodynamics. The particle picture is what appears in particular measurements and calculations. The field picture is the underlying framework. Gluons are especially interesting because they carry color charge, the type of charge involved in the strong interaction. Color charge is not ordinary color. A quark is not literally red, green, or blue in the way paint or light can be red, green, or blue. The names are labels for a mathematical property. Still, the naming does make the strong force sound slightly more artistic than expected, as though the deepest structure of matter is being held together by an extremely serious paint set. The important point is that gluons respond to the same kind of charge they carry, which makes the strong interaction very different from electromagnetism. One of the great consequences of this behavior is confinement. Under ordinary conditions, isolated quarks are not observed. Quarks are found bound inside particles such as protons, neutrons, and other hadrons. If energy is added in an attempt to separate quarks, the energy in the strong field can produce new particles, rather than allowing a single free quark to emerge. This is very different from electromagnetism, where electric forces generally weaken as charged objects are separated. The strong force has a more stubborn character. It does not politely fade in the same simple way. It binds quarks so tightly that the particles inside atomic nuclei remain stable across the ordinary conditions of the universe. But the strong interaction does not matter only inside individual protons and neutrons. It also helps atomic nuclei hold together. Protons all carry positive electric charge, so electromagnetism makes them repel one another. In a nucleus, that repulsion is real, yet protons and neutrons can remain bound because of the residual strong nuclear force. This is not the full quark binding force in the same direct form, but a leftover effect of the strong interaction between protons and neutrons. It operates over very short distances, roughly the scale of an atomic nucleus, but within that tiny range it is powerful enough to hold nuclear matter together. This is what makes atoms beyond hydrogen possible. Hydrogen has the simplest nucleus, usually just one proton, but helium, carbon, oxygen, iron, calcium, and all heavier elements require nuclei containing multiple protons and neutrons. Without the strong force, the positive charges in those nuclei would fly apart. There would be no carbon chemistry, no oxygen to breathe, no calcium in bones, no iron in blood, no silicon in rocks, and no gold sitting around looking unnecessarily pleased with itself. The richness of matter depends on the ability of atomic nuclei to exist. The strong interaction is also tied to the history of the elements. In stars, nuclear fusion combines light nuclei into heavier ones, releasing energy and allowing stars like the sun to shine. Stellar nucleosynthesis builds many elements through nuclear reactions in stellar cores. More extreme events, including supernova explosions and neutron star mergers, help produce and distribute heavier elements into space. The material that later becomes planets, oceans, living cells, and human hands has been shaped by nuclear processes, all relying on the forces that govern atomic nuclei. So quantum fields help create reality not only by producing particles as excitations, but by allowing those particles to bind into stable structures. Quark fields and gluon fields are not remote details hidden in particle accelerators. They are part of why the center of every atom can hold together. They help make nuclei possible, and nuclei make complex atoms possible. From there, chemistry can unfold, stars can forge elements, planets can form, and the visible world can become textured, heavy, varied, and alive with structure. At the deepest level, matter is not merely assembled, it is held together by fields. The weak nuclear interaction is quieter than the strong force in one sense, but its consequences reach across stars, atoms, radioactivity, and the slow transformation of matter. It does not hold nuclei together in the same direct way as the strong interaction, and it does not shape everyday chemistry as visibly as electromagnetism. Instead, the weak force is involved in certain kinds of change. It allows particles to transform into other particles. It is one of the deep reasons the universe is not frozen into one unchanging arrangement, but can gradually shift, decay, fuse, and evolve. One of the most important examples is beta decay. In beta decay, an unstable atomic nucleus changes by transforming one of its particles. A neutron can change into a proton, releasing an electron and an antineutrino. In another form, a proton can effectively change into a neutron under the right conditions. Beneath this nuclear language, the weak interaction can change one type of quark into another. A down quark can become an up quark, or an up quark can become a down quark, depending on the process. Since protons and neutrons are made from up quarks and down quarks, this quark-level transformation changes the identity of the larger particle. That is a remarkable thing. The weak interaction does not simply push or pull, it changes what a particle is. It allows the composition of matter to alter in a controlled way, according to quantum rules. In ordinary life, a chair does not turn into a slightly different chair, because one of its inner ingredients had a thoughtful moment. But inside nuclei, over timescales ranging from fractions of a second to billions of years, weak processes can reshape matter. Radioactive decay, nuclear reactions, and some of the universe's most important energy-producing processes depend on this ability. The weak interaction is associated with fields whose excitations are the W bosons and Z bosons. These particles are far heavier than electrons or photons, and because of their large mass, the weak force acts over an extremely short range. Its influence is limited to distances much smaller than an atomic nucleus. That is one reason it does not appear in everyday experience as a familiar push, pull, or glow. But at the scale of particles, it is essential. The W boson is involved in charged weak interactions, where electric charge can be exchanged and particle identities can change. The Z boson is involved in neutral weak interactions, where the charge does not change in the same way. An early theory of beta decay was developed by Enrico Fermi in the 1930s. Fermi's theory was a major step toward understanding weak processes, even though the later field-based picture became more complete. In the 20th century, Sheldon Glashow, Abdus Salam and Steven Weinberg developed electroweak theory, which showed that the electromagnetic force and weak force are related aspects of a deeper unified framework. At very high energies, they behave as parts of one electroweak interaction. At lower energies, such as those in ordinary present-day life, they appear as separate forces, partly because of the role of the Higgs field. The weak force is also involved in the Sun's ability to shine. In the Sun's core, hydrogen nuclei undergo a chain of nuclear reactions that gradually build helium. The first step in the main proton-proton chain requires one proton to transform into a neutron, forming deuterium. That transformation depends on the weak interaction. Without it, the Sun's fusion process would be very different, and stars like the Sun would not shine in the same steady way. The sunlight warming Earth depends in part on one of the subtlest interactions in particle physics. It is a gentle reminder that even a sunny afternoon has some extremely complicated paperwork hidden underneath. The weak interaction also matters for neutrinos, those light and elusive particles produced in many weak processes. Trillions of solar neutrinos pass through a human body every second, almost all of them continuing through Earth as though the planet were barely there. They are difficult to detect because they interact so weakly with matter, but they carry information about nuclear reactions in the Sun, supernovae, and other high-energy environments. So quantum fields do not only create stable structures, they also govern transformation. The electron field, quark fields, and photon field help explain matter and light, while the weak interaction shows how matter can change identity at the most fundamental levels. Stars shine, nuclei decay, elements shift, and particles transform because fields interact according to precise rules. Reality is not just built from fields, it is continually edited by them, slowly and carefully, in ways that allow the universe to glow, age, and become chemically rich. The Higgs field is one of the strangest parts of modern physics because it is not simply another field producing another kind of particle. It changes the properties of other particles. It is present throughout space, even in what would otherwise seem like emptiness, and it has a non-zero value everywhere. This means the Higgs field is not switched off in empty space. It is quietly there, part of the background structure of the universe, influencing how certain fundamental particles behave. The basic idea is that some particles interact with the Higgs field, and through that interaction they acquire mass. The stronger the interaction, the more mass the particle has. Particles that do not interact with the Higgs field in this way, such as photons, remain massless. A photon has energy and momentum, but no rest mass, which is why light travels through vacuum at the speed of light. Electrons, quarks, W bosons and Z bosons, however, do interact with the Higgs field, and that interaction is part of why they have mass. This does not mean the Higgs field gives all mass to everything, which is a common and understandable simplification. The Higgs field gives fundamental particles such as electrons and quarks their intrinsic masses. But most of the mass in ordinary matter comes from protons and neutrons, and most of the mass of protons and neutrons comes not from the bare masses of the quarks inside them, but from the energy of the strong interaction. The motion of quarks, the behavior of gluon fields, and the energy stored in that intense quantum system contribute most of the mass in the atoms around us. So the Higgs field is essential, but it is not the universe's only mass-making department. Physics, apparently, prefers committees. The Higgs mechanism was developed in the 1960s by several scientists working on related ideas. Peter Higgs is the name most famously attached to it, but François Englert, Robert Brute, Gerald Guralnick, Carl Hagen, and Tom Kibble were also key figures. Their work helped explain how certain force-carrying particles could have mass without breaking the mathematical consistency of the theory. This was especially important for the weak interaction, whose W bosons and Z bosons are massive, unlike the massless photon of electromagnetism. The Higgs field is also closely tied to electroweak theory, the framework developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg that showed electromagnetism and the weak interaction are related aspects of a deeper electroweak force. In the early universe, at extremely high energies, these forces are thought to have behaved in a more unified way. As the universe cooled, the Higgs field took on its non-zero value, a process connected with electroweak symmetry breaking. After that, the electromagnetic and weak interactions appeared distinct, and particles such as the W boson and Z boson gained mass through their interaction with the Higgs field. The Higgs boson is not the Higgs field itself. It is an excitation of the Higgs field, just as a photon is an excitation of the electromagnetic field. This distinction matters. The field is the deeper entity present throughout space. The boson is the particle-like ripple that can appear when the field is excited in a particular way. Detecting the Higgs boson was therefore a way of confirming that the Higgs field was not just a clever theoretical idea, but part of physical reality. In 2012, scientists at CERN announced the discovery of a new particle consistent with the Higgs boson. This discovery came from experiments at the Large Hadron Collider, the enormous particle accelerator near Geneva, using the ATLAS and CMS detectors. Protons were accelerated to extremely high energies and collided, creating conditions where new particles could briefly appear. The Higgs boson itself decays almost immediately, so scientists did not see it sitting neatly in a detector like a tiny trophy. Instead, they identified it through the patterns of particles produced by its decay. It was a delicate reconstruction, more like finding the footprint of something that vanished almost as soon as it arrived. The discovery mattered because it completed a central missing piece of the standard model of particle physics. It confirmed that the Higgs mechanism described something real about nature. It showed that empty space is not merely a passive absence, but can contain a field whose value affects the masses of fundamental particles. This brings the question of reality into sharper focus. Quantum fields do not simply exist side by side like separate invisible layers. They interact. One field can shape the behavior of another. The Higgs field changes the basic properties of particles arising from other fields, helping decide whether they have mass and how they participate in the structure of matter. Reality depends not only on fields existing, but on their relationships. The world has weight, stability, atoms, chemistry, and form because fields do not merely fill the universe. They speak to one another, and their quiet conversation helps make the universe what it is. Empty space sounds like the simplest thing in the universe. It sounds like absence. No air, no dust, no atoms, no light, no drifting specks, no hidden furniture waiting to be discovered with a better torch. In everyday language, a vacuum means that something has been removed. A bottle can be emptied, a room can be cleared, space can seem blank. The mind naturally imagines nothingness as a quiet, passive gap between things. Quantum field theory makes that picture much stranger. In this deeper view, empty space is not empty in the ordinary sense. It is not filled with normal particles, like a thin mist of invisible dust. It is not packed with tiny marbles waiting to become matter, but it is still structured by fields. The vacuum, in quantum field theory, is the lowest energy state of those fields. It is the condition fields settle into when there are no real particles present. That means the vacuum is not a simple nothing. It is the ground state of a field-based universe. This is a careful distinction, but an important one. When physicists speak about the quantum vacuum, they do not usually mean a place where absolutely nothing exists. They mean a state with no detectable particles of a particular kind, while the underlying fields remain present. The electron field is still part of the description. The electromagnetic field is still part of the description. The quark fields, gluon fields, Higgs field and other fields do not vanish simply because a region contains no ordinary matter. Empty space is not a blank page. It is more like a page on which the ink has not yet formed letters, while the paper itself remains quietly there. Even in the lowest possible state, quantum fields can have what is called zero-point energy. This is the remaining quantum activity associated with a field, even when it has no ordinary particles in it. A classical system might be imagined as perfectly still at its lowest energy, like a pendulum hanging motionless at the bottom of its swing. But quantum systems do not always allow that kind of perfect stillness. Because of the uncertainty principle, certain properties cannot both be pinned down with unlimited precision. The result is that the ground state of a field is not always a state of absolute dead calm. This is where vacuum fluctuations enter the story, and this is also where the language can become misleading. It's often said that particles are constantly popping in and out of existence in empty space. That image is memorable, but it can be too cartoonish if taken literally. The quantum vacuum is not simply a fizzing soup of tiny real particles appearing like bubbles in a drink. Vacuum fluctuations are better understood as features of quantum fields and their possible disturbances, reflected in calculations and measurable effects. They're not ordinary particles that can be scooped up and placed in a jar, which is probably for the best, because jars have suffered enough in physics explanations. One famous phenomenon linked with the quantum vacuum is the Casimir effect. Hendrik Casimir predicted that two closely spaced conducting plates in a vacuum could experience a tiny attractive force. The basic idea is that the presence of the plates changes which electromagnetic field modes are allowed between them compared with outside them. This difference can produce a measurable force. It is extremely small and delicate, but it shows that what is called empty space can have physical consequences when boundaries and quantum fields are involved. Another important clue comes from the Lamb shift, named after Willis Lamb. In hydrogen atoms, energy levels that early theory suggested should be identical were found to be slightly different. Quantum electrodynamics explained this shift through interactions involving the electron, the electromagnetic field, and vacuum-related effects. The Lamb shift became one of the great successes of quantum electrodynamics, showing that tiny corrections from field behavior could be measured in atomic spectra. Even the quiet structure of empty space could leave fingerprints on the light emitted by atoms. These effects do not mean the vacuum is a magical energy source or a hidden ocean of free power. The quantum vacuum is a precise scientific idea, not a cosmic battery waiting for someone with an overconfident screwdriver. Its behavior is subtle, constrained, and described through carefully tested theory. But it does mean that apparent nothingness has structure. The absence of ordinary particles is not the same as the absence of fields. This brings the question of quantum fields and reality into a deeper place. Fields do not only produce particles when they are excited, they also define what emptiness itself means. The stage on which matter appears is not truly blank. It has ground states, possible excitations, measurable effects, and relationships with atoms and boundaries. Even when the universe seems empty, quantum fields remain part of the physical description. So if quantum fields help create reality, they do so not only by giving rise to matter and light, but by shaping the meaning of absence itself. Empty space is not a silent nothing beneath the world. It is the lowest whisper of fields that are still there, quietly setting the conditions from which particles, forces, atoms, and visible reality can appear. The standard model of particle physics is the closest thing modern science has to an inventory of the known microscopic world. It is not a list of everything that exists, and it is not a final theory of reality, but it is extraordinarily successful. It describes the known fundamental particles and 3 of the 4 fundamental interactions: electromagnetism, the strong nuclear interaction, and the weak nuclear interaction. Gravity, described so beautifully by general relativity, sits outside this framework, which is one reason the story remains unfinished. At first glance, the standard model can look like a catalogue of particles. There are quarks, leptons, gauge bosons, and the Higgs boson. The names can make it sound like physics is introducing a cast of characters from a very niche theatre production, where everyone has spin, charge, and no interest in being intuitive. But beneath the list of particles is a deeper field-based picture. Each kind of fundamental particle corresponds to an underlying quantum field. The particles are the excitations. The fields are the structures that make those excitations possible. The matter particles are grouped into quarks and leptons. Quarks include up quarks and down quarks, which help form protons and neutrons, along with heavier quarks that appear in high-energy processes and decay quickly. Leptons include the electron, the muon, the tau particle, and their associated neutrinos. The electron is the lepton most familiar to everyday life, shaping atoms, chemistry, electricity, and biological processes. Neutrinos are much harder to catch. They interact so weakly that vast numbers of them pass through Earth and through human bodies, almost without noticing that matter is there at all. The force-carrying particles are called gauge bosons. The photon is associated with the electromagnetic field. Gluons are associated with the strong interaction. The W bosons and Z boson are associated with the weak interaction. These particles are not little mechanical tools being passed around in a simple classical machine. They are excitations of fields that describe how interactions happen. The Standard Model is powerful because it links particles, fields, symmetries, and forces into one mathematical framework. It does not merely say what exists, it describes how the known pieces of microscopic reality behave together. The Higgs field occupies a special place in this inventory. It is not a matter field like the electron field, and it is not a force field in the same sense as the electromagnetic or gluon fields. Its non-zero value throughout space helps give certain fundamental particles their mass through the Higgs mechanism. The Higgs boson, discovered in 2012, is the particle-like excitation of this field. Its discovery confirmed that an invisible field spread through empty space could have direct consequences for the basic properties of particles. Testing the Standard Model requires experiments that reach far beyond ordinary human scale. Particle accelerators create high-energy collisions, allowing physicists to probe small distances and produce particles that do not usually appear in everyday conditions. At CERN, the Large Hadron Collider has tested the Standard Model with extraordinary precision, using detectors such as ATLAS and CMS. Earlier machines, including the Large Electron-Positron Collider, helped refine measurements of the weak interaction and the Z boson. Fermilab in the United States and Brookhaven National Laboratory have also played major roles in particle physics, from studying quarks and neutrinos to testing the magnetic behavior of muons. These experiments do not observe fields directly in the everyday sense. A detector does not display a glowing label saying, "Congratulations, you have found a quantum field." Instead, detectors record tracks, energies, decay products, flashes of light, and electrical signals. Physicists reconstruct what happened by comparing those patterns with the predictions of quantum field theory. When the predictions match again and again across many particles and interactions, confidence grows that the field-based description is capturing something real about nature. But the Standard Model is incomplete. It does not include a complete quantum theory of gravity. It does not explain what dark matter is. It does not fully explain dark energy. It leaves open questions about why neutrinos have mass, why the universe contains much more matter than antimatter, and why the constants of nature have the values they do. It is a brilliant map, but it is not the whole territory. Some regions are still blank, and some may require entirely new ideas. Still, the lesson it offers is profound. The most precise inventory of known reality is not mainly an inventory of solid objects. It is an inventory of fields and their excitations, of interactions and symmetries, of patterns that become measurable as particles, forces, mass, and light. The Standard Model suggests that the world is not built from tiny things alone. It is built from fields behaving according to rules so consistent that, at larger scales, they become atoms, stars, planets, chemistry, and the quiet everyday world that seems so simple until physics looks underneath. Symmetry sounds at first like a visual idea. A snowflake has symmetry. A butterfly has symmetry, if it is feeling cooperative and sitting still. A circle looks the same when rotated. A mirror can turn left into right, and make a room feel slightly more mysterious than necessary. But in modern physics, symmetry means something deeper than visual balance. It means a regularity in the laws of nature, a transformation that can be made without changing the essential physics. For example, if an experiment gives the same result today as it would tomorrow under the same conditions, there is a symmetry in time. If the same experiment works the same way in one place as it does in another, there is a symmetry in space. If turning an experiment around does not change the underlying laws, there is a symmetry in direction. These may sound like quiet assumptions, but they are profound. They suggest that nature is not rewriting its rules from moment to moment or place to place. The universe is strange, yes, but at least it is not changing the instructions every Tuesday. One of the most important figures in understanding symmetry was Emmy Noether. In the early 20th century, Noether proved a theorem showing that continuous symmetries are connected to conservation laws. This result, known as Noether's theorem, is one of the great achievements of theoretical physics. If the laws of physics do not change over time, energy is conserved. If the laws do not change from one place to another, momentum is conserved. If the laws do not change under rotation, angular momentum is conserved. Conservation laws are not just convenient bookkeeping rules. They're connected to the deep symmetry structure of reality. This matters enormously for quantum fields. In quantum field theory, symmetries are not decoration added after the particles have been chosen. They help decide which fields exist, how those fields interact, and what kinds of particles and forces appear. The Standard Model is built around symmetry principles. Its mathematical structure depends on the idea that certain transformations can be made without changing the observable physics. These symmetries place strict limits on what particles can do, which interactions are allowed, and how forces behave. Gauge symmetry is especially important. It is a defining principle behind the electromagnetic, weak, and strong interactions in the Standard Model. Gauge symmetry is a more abstract kind of symmetry than the rotation of a snowflake or the reflection of a face. It involves changes in the mathematical description of fields that leave the physical situation unchanged. This may sound as if physics is protecting itself from its own paperwork, but the result is very real. When gauge symmetry is made part of the theory, force fields naturally appear. Electromagnetism, the weak interaction, and the strong interaction are deeply tied to these gauge symmetries. The electromagnetic field is connected with one kind of gauge symmetry. The strong interaction, described by quantum chromodynamics, is connected with a more complex gauge symmetry involving color charge. The weak interaction is also part of this gauge-based structure, and at high energies it is joined with electromagnetism in electroweak theory. These are not merely labels, they are rules that shape how fields behave. They help explain why photons, gluons, W bosons, and Z bosons have the roles they do in the microscopic world. But symmetry can also be broken, and this is where reality becomes especially interesting. A law can have symmetry even when the state of a system does not show it clearly. This is called spontaneous symmetry breaking. A simple way to imagine it is a round table with many equally valid directions and a pencil balanced upright at the center. The setup is symmetrical, but once the pencil falls, it chooses one direction. The underlying situation allowed all directions equally, but the final state does not display that symmetry. The symmetry is hidden, not absent. In particle physics, spontaneous symmetry breaking is central to the Higgs field and electroweak theory. At very high energies, electromagnetism and the weak interaction are understood as parts of a unified electroweak framework. As the universe cooled, the Higgs field settled into a non-zero value throughout space. This changed how particles interacted with the field, giving mass to W bosons and Z bosons while leaving the photon massless. The symmetry of the deeper theory was still part of the mathematics, but the low-energy universe no longer displayed it in the same obvious way. This means the properties of reality are not arbitrary decorations. Mass, charge, interaction rules, conservation laws, and the behavior of particles are all tied to mathematical structure. Quantum fields do not create reality only by producing particle-like excitations. They help create reality through rules, patterns, permissions, and restrictions. They define what can happen, what must be conserved, what can transform, and what remains forbidden. The world feels solid and immediate, but beneath that surface it is shaped by symmetry. The familiar universe is not simply a pile of particles. It is a field-based structure governed by deep regularities, some visible, some hidden, and some broken in ways that made stars, atoms, and ordinary matter possible. Reality has a shape, even before it has an object. Measurement is one of the most delicate ideas in quantum theory, because it touches the boundary between possibility and fact. Before a measurement, a quantum system is often described in terms of probabilities. It may have several possible outcomes, each with a calculable chance of being observed. After a measurement, however, one outcome is recorded. A detector clicks, a mark appears, a photon is absorbed, an electron is found in one place rather than another. The gentle mystery is not that experiments give results. They clearly do. The mystery is how the many possibilities described by the theory become the single result that reality presents. This is known as the measurement problem. It's sometimes described in dramatic ways as if the universe waits for a conscious mind to glance at it before deciding what to be. That can make a good headline, but it is not the careful scientific version. The measurement problem asks how the smooth, probability-based description of a quantum system relates to the definite outcomes seen in experiments. Quantum theory can calculate the probabilities with extraordinary accuracy, but explaining exactly what happens during measurement remains one of the deepest conceptual questions in physics. In the standard quantum picture, a system can exist in a superposition, meaning its state includes multiple possible measurement outcomes at once. An electron, for example, may be described by a wave function that gives different probabilities for where it might be detected. But when an actual measurement occurs, the result is definite. The electron is found here, not there. The screen shows one mark, not a gentle cloud of maybes politely spread across the room. The mathematics predicts the pattern of many such results, but the transition from possibility to outcome is where interpretation enters. The Copenhagen interpretation, associated especially with Niels Bohr and Werner Heisenberg, became one of the most influential ways of thinking about this. In broad terms, it treats the wave function as a tool for predicting measurement outcomes, rather than as a simple picture of a physical object moving along a hidden classical path. Bohr emphasized the importance of experimental arrangements and the limits of applying everyday concepts to quantum systems. Heisenberg's uncertainty principle reinforced the idea that certain properties are not merely unknown before measurement, but cannot all be assigned definite classical values at the same time. The Copenhagen interpretation helped physicists use quantum theory with great success, but it did not end debate. Other interpretations exist, including many worlds, pilot wave theory, objective collapse models, and relational approaches. These interpretations often agree on the experimental predictions, but disagree about what the theory means beneath the calculations. This is one reason quantum physics can feel so strange. It is not vague in its predictions. It is vague, or at least unsettled, in the story humans tell about what those predictions reveal. A modern idea that helps explain part of the puzzle is decoherence. Decoherence describes how quantum superpositions become effectively unobservable when a system interacts with its environment. H. Dieter Zeh and Wojciech Zurek made important contributions to this field. A tiny quantum system can maintain delicate relationships between possible states under controlled conditions, but when it becomes entangled with countless surrounding particles, such as air molecules, photons, dust, heat, and measuring equipment, those delicate relationships spread into the environment. The system no longer behaves for practical purposes, like a clean superposition that can show interference. This helps explain why everyday objects do not appear in obvious superpositions. A chair does not sit in two corners of a room at once, at least not without causing a very serious furniture issue. Large objects interact constantly with their environments. Their quantum possibilities become entangled with so many surrounding degrees of freedom that interference between alternatives becomes effectively impossible to observe. Decoherence does not solve every philosophical aspect of the measurement problem, but it explains why the classical world emerges so reliably from quantum ingredients. Quantum field theory works beautifully within this measured world. It predicts scattering events, decay rates, energy shifts, magnetic properties, and particle interactions with remarkable precision. In particle physics, what detectors record are definite outcomes: tracks, flashes, energies, and decay products. The field equations provide probabilities for those outcomes, and experiments compare those probabilities with real data. Even if the deepest interpretation of measurement remains subtle, the practical success of the theory is not in doubt. This matters for the question of whether quantum fields create reality. Fields may underlie particles, matter, light, and forces, but observed reality is also shaped by interaction. A field excitation becomes known through what it does to something else. A photon is detected when it's absorbed. An electron is measured when it interacts with a detector. The world that appears definite is not separate from quantum fields, but it is also not a simple frozen picture of them. It emerges through probabilities, environments, measurements, and the steady narrowing of many possible outcomes into the one experienced result. Reality, then, is not merely a set of fields existing silently beneath everything. It is fields interacting, fields becoming entangled, fields leaving traces, and fields producing stable patterns that can be observed. The world feels definite because quantum possibilities do not remain isolated forever. They meet environments, instruments, atoms, eyes, and eventually memory. Somewhere in that long chain, the strange language of probability becomes the familiar language of what happened. Quantum fields are often introduced through particles, atoms, and laboratory experiments, but their reach is much larger than the microscopic world. They're also part of the way modern cosmology describes the early universe. The same field-based thinking that helps explain electrons, photons, quarks, and the Higgs boson also appears when physicists ask how the universe grew from an extremely hot, dense beginning into a cosmos filled with galaxies, stars, planets, and the quiet possibility of someone wondering about all of this under a blanket. In its earliest known stages, the universe was not filled with atoms because atoms had not yet formed. There were no stars, no galaxies, no planets, no chemistry in the familiar sense, and no little pockets of cosmic scenery waiting around to become picturesque. The early universe was extremely hot and dense, a state where particles and radiation interacted intensely. At high enough energies, the distinctions between some forces may have been different from what they are today, and quantum fields would have been central to describing what existed and how it behaved. This is important because quantum field theory is not only a theory of tiny objects inside today's universe, it is also a theory of fields that fill space-time, and in the early universe, space-time itself was changing rapidly. Conditions were so extreme that the universe must be described using both particle physics and cosmology. The physics of fields was not hidden away inside atoms. It was part of the entire cosmic environment. One of the leading ideas about the very early universe is cosmic inflation. Inflation proposes that for a very brief period, the universe expanded at an extraordinarily rapid rate. The idea was developed in important ways by Alan Guth in the early 1980s and later by Andre Linde and others. inflation was proposed to help explain several puzzles, including why the observable universe looks so uniform on large scales, why space appears so close to flat, and why distant regions of the cosmic microwave background have nearly the same temperature, even though they seem too far apart to have exchanged information in a simple non-inflationary picture. The exact mechanism behind inflation is still uncertain. Many models involve a hypothetical field often called the inflaton field. In these models, the energy associated with this field drives the rapid expansion. The inflaton has not been directly detected, and inflation is not a single completed theory with every detail settled. It is better understood as a broad family of models, some more strongly supported than others, all trying to describe a very early phase of cosmic history. One of the most fascinating ideas linked to inflation is that quantum fluctuations may have been stretched to cosmic scales. In ordinary quantum field theory, fields have fluctuations even in their lowest states. During inflation, tiny differences in field values could have been stretched enormously as space expanded. Over time, these stretched fluctuations could become small differences in density. Later, gravity could amplify those differences, helping matter gather into the large-scale structure of the universe. Galaxies, clusters of galaxies, and the vast cosmic web may have roots in quantum variations from the universe's earliest moments. This is one of the most profound connections in science. The same quantum principles that make the microscopic world uncertain may have helped write the first faint pattern from which the cosmic structure grew. A tiny early fluctuation, once stretched and preserved, could become part of the reason matter later collected here rather than there. It is not that quantum fields simply made galaxies appear fully formed, politely labelled and ready for telescopes. Rather, field fluctuations may have supplied the seeds that gravity slowly cultivated across billions of years. The strongest observational window into the early universe is the cosmic microwave background. This is the ancient afterglow from a time when the universe cooled enough for electrons and atomic nuclei to combine into neutral atoms, allowing light to travel freely. That light has been stretched by cosmic expansion into microwave radiation. Space missions such as COBE, WMAP, and the Planck Space Observatory measured this background with increasing precision. They found it to be remarkably uniform, but not perfectly smooth. Tiny temperature variations in the cosmic microwave background reveal early density differences that later grew into cosmic structure. These observations strongly support the idea that the early universe was hot, dense, expanding, and filled with tiny irregularities that became the seeds of later structure. They also fit many predictions of inflation, though they do not prove every detail of inflation or identify the exact field responsible. The science is powerful but still incomplete. The broad picture of an evolving universe is well supported. The precise physics of its earliest fractions of a second remains one of the great open frontiers. So quantum fields may not only describe small particles in detectors or atoms in matter, they may also help explain why the observable universe has structure at all. If fields shaped the earliest moments, and if their fluctuations became the starting points for galaxies, then quantum fields are not merely ingredients of reality at the smallest scales. They may also be part of the reason the largest structures in the universe exist, turning microscopic uncertainty into the vast architecture of the cosmos. Gravity is the great unfinished doorway in the field-based picture of reality. The Standard Model describes electromagnetism, the strong nuclear interaction, and the weak nuclear interaction through quantum fields with extraordinary success. It gives physics a precise language for particles, forces, decays, collisions, and the hidden structures inside atoms. But gravity does not fit neatly into that same framework. It is everywhere, shaping planets, stars, galaxies, black holes, and the expansion of the universe, yet it remains the major interaction not fully integrated into the standard model's quantum field description. Albert Einstein's general relativity, completed in the early 20th century, describes gravity in a very different way from the other forces. In Newton's picture, gravity was a force pulling masses toward one another. In general relativity, gravity is not quite a conventional force. It is the curvature of space-time caused by energy and mass. Matter tells space-time how to curve, and curved space-time tells matter how to move. A planet orbiting a star is not simply being tugged across empty space. It is following a path through space-time whose geometry has been shaped by the star's mass and energy. This idea has been tested again and again. General relativity explains the precession of Mercury's orbit, the bending of starlight by the sun, the slowing of time in gravitational fields, the behavior of neutron stars, and the gravitational waves detected by LIGO and Virgo from merging black holes and neutron stars. It is one of the most successful theories ever created. It is also deeply elegant, in that mildly annoying way great theories sometimes are, where the universe appears to have been hiding a geometric masterpiece behind falling apples. But general relativity and quantum field theory describe reality in very different languages. Quantum field theory usually works on a space-time background. Fields exist and interact within space-time, and particles appear as excitations of those fields. In many calculations, space-time is treated as the stage on which quantum events happen. General relativity, however, says the stage is not fixed. Space-time itself bends, stretches, responds, evolves, and carries gravitational waves. It is not just the place where physics happens, it is part of the physics. This creates a deep problem. If quantum fields are part of reality, and space-time itself is dynamic, then what happens when space-time must also obey quantum rules? Near black holes, gravity becomes extremely strong. Near the Big Bang, or whatever deeper early state preceded the familiar expansion, the universe was extremely dense and hot. In such places, quantum effects and strong gravity may both matter at once. General relativity alone is likely incomplete there. Ordinary quantum field theory alone is also not enough. The two great frameworks need to be reconciled, but doing so has proved extraordinarily difficult. Physicists often speak of quantum gravity as the missing theory that would describe gravity in quantum terms. One simple hope might be to treat gravity like the other interactions, with a hypothetical particle called the graviton as the quantum excitation of the gravitational field. This idea is useful in some limited settings, especially when gravity is weak. But a full theory of quantum gravity has to do more than add another particle to the standard model's family gathering. It has to explain the quantum nature of space-time itself. Several approaches have been explored. String theory suggests that the fundamental ingredients of nature may not be point-like particles, but tiny vibrating strings, with different vibrations corresponding to different particles. In many versions, gravity appears naturally, which is one reason the theory has attracted so much attention. Loop quantum gravity takes a different path, attempting to quantize space-time geometry itself, suggesting that areas and volumes may have discrete quantum structure at extremely tiny scales. Both approaches are serious attempts to understand quantum gravity, but neither has been confirmed experimentally as the final theory. Stephen Hawking gave one of the most famous clues that quantum fields and gravity cannot be kept fully separate. In the 1970s, he showed that when quantum field theory is considered in the curved space-time near a black hole, black holes should emit radiation. This is now called Hawking radiation. The effect is expected to be incredibly faint for ordinary astrophysical black holes, far too weak to detect directly with present technology, but it is conceptually profound. Black holes, once thought to be completely black, may slowly lose energy through quantum effects near their event horizons. Hawking radiation does not complete quantum gravity, but reveals the tension beautifully. It involves quantum fields, curved space-time, thermodynamics, and black holes all at once. It hints that the deepest description of reality must somehow include both the field-based world of quantum theory and the geometric world of general relativity. So quantum fields may explain much of known reality, from particles and forces to light, atoms, and the structure of empty space. But the story is not complete. Gravity still waits at the edge of the framework, bending the stage on which fields appear. Until space-time and gravity are understood at the quantum level, the question of whether quantum fields create reality remains powerful but unfinished. The fields may build much of the visible world, yet the arena in which they exist may have a deeper quantum nature still waiting to be understood. The known fields of the Standard Model explain an extraordinary amount, but the universe is not polite enough to stop there. When astronomers look outward, the visible cosmos gives hints that the current inventory of particles and fields is incomplete. Stars, gas, dust, planets, and glowing galaxies are only the easiest parts to notice. A little like judging an entire ocean by the foam on the waves. Two of the greatest clues that something deeper remains hidden are called dark matter and dark energy. Dark matter is not called dark because it is gloomy, suspicious, or dressed for a very formal evening. It is called dark because it does not emit, absorb, or reflect ordinary light in a way that makes it directly visible through telescopes. Its presence is inferred from gravity. Galaxies rotate in ways that cannot be explained by the visible matter alone. Galaxy clusters hold together more strongly than expected from the stars and gas that can be seen. Light from distant objects is bent by gravity in a process called gravitational lensing, revealing mass that does not shine. The large-scale structure of the universe also points toward an unseen component helping matter gather over cosmic time. Vera Rubin and Kent Ford played a crucial role in strengthening the evidence for dark matter through observations of galaxy rotation curves. In many spiral, galaxies, stars far from the centre, orbit faster than expected if only visible matter were present. Instead of dropping off neatly with distance, the rotation speeds remain unexpectedly high. This suggested that galaxies are surrounded by much larger halos of unseen mass. Later evidence from gravitational lensing, galaxy cluster observations, and the cosmic microwave background made the case broader and stronger. Dark matter is not just one odd measurement. It is a pattern appearing across many parts of cosmology. Yet dark matter has not been directly identified. It may be made from a particle or particles beyond the Standard Model. Some possibilities are field-related. Axions are hypothetical light particles originally proposed in connection with a problem in quantum chromodynamics. Weakly interacting massive particles are another long-discussed possibility, though experiments have not yet found them. Sterile neutrinos have also been considered as a possible hidden kind of neutrino that would interact even less than the familiar ones. These ideas remain hypotheses. They are serious scientific candidates, but none has been confirmed as the answer. Dark energy is a different mystery. It is the name given to whatever is driving, or at least describing, the apparent accelerated expansion of the universe. In the late 1990s, observations of distant supernovae by the Supernova Cosmology Project and the High Z Supernova Search Team showed that the expansion of the universe was not slowing down as expected. It was speeding up. This discovery was surprising enough to make cosmology quietly put down its cup of tea and stare at the wall for a moment. The simplest explanation for dark energy is the cosmological constant. a term associated with Albert Einstein's equations of general relativity. In modern cosmology, it can be thought of as a constant energy density associated with space itself, but the deeper nature of dark energy remains unknown. There are also field-based ideas, such as quintessence, which proposes a dynamic field whose energy changes over time and could drive accelerated expansion. Quintessence has not been confirmed, and present observations are still consistent with a cosmological constant. The mystery is not solved merely because it has a tidy name. Together, dark matter and dark energy make up most of the universe's total energy budget in the standard cosmological model. Ordinary matter, the stuff of stars, planets, people, oceans, and slightly overconfident biscuits, is only a small fraction. That fact is humbling. The fields and particles described by the standard model are incredibly successful, yet they appear to describe only part of the full cosmic inventory. This matters for the question of whether quantum fields create reality. If known quantum fields underlie ordinary matter, light, and familiar forces, then unknown fields may also shape the universe in ways not yet understood. Dark matter may involve a new field or a new particle excitation. Dark energy may involve the vacuum, a cosmological constant, or a field-like phenomenon beyond current confirmation. The answer is still open. The visible world may therefore be one region of a much larger physical story. Quantum fields help explain the reality that can be touched, seen, measured, and built into atoms. But the cosmos also points toward hidden mass, accelerated expansion, and missing ingredients. If fields create much of known reality, then some of reality may still be waiting for its fields to be discovered. So, do quantum fields create reality? The most careful answer is yes, in a scientific sense, but not in a mystical one. Quantum fields do not create reality because someone looks at the universe, thinks about it, or believes in it with unusual enthusiasm. They are not a magical source from outside nature. They are part of nature's deepest known description. In modern physics, quantum fields are among the fundamental physical ingredients from which particles, forces, matter, light, and many measurable properties of the observable universe emerge. This answer matters because the word create can easily wander into strange territory. It can suggest that the universe is imaginary, or that consciousness is somehow painting matter into existence moment by moment. That is not what quantum field theory says. The theory does not make the world less real. It makes the world more deeply structured than everyday perception suggests. The table still holds the cup, the floor still supports the room, light still reaches the eye. But beneath these familiar experiences, physics finds fields, interactions, symmetries, quantum states, and patterns of energy. The journey begins with the older picture of solid matter moving through empty space. Newton's mechanics made that picture powerful, describing motion and gravity with astonishing success. Faraday and Maxwell then changed the meaning of space by showing that fields could be real physical features, not just convenient ideas. Electric and magnetic fields filled space, influenced matter, and carried light as electromagnetic waves. Long before quantum field theory, physics had already learned that invisible structure could be part of reality. Then classical certainty began to crack. Blackbody radiation, the photoelectric effect, atomic spectra, and the stability of atoms reveal that matter and light were not behaving according to smooth classical rules alone. Max Planck introduced the quantum idea. Albert Einstein showed that light could behave as packets of energy. Niels Bohr proposed discrete atomic energy levels. Louis de Broglie suggested that matter itself had wave-like properties. Schrödinger and Heisenberg built quantum mechanics, showing that probability, wave functions, uncertainty, and measurement were not minor details but central features of microscopic nature. Special relativity then added another demand. A deeper theory had to respect the speed of light, space-time, and the relationship between mass and energy. Ordinary quantum mechanics worked wonderfully for many atomic systems, but it often assumed a fixed number of particles. Nature does not always behave so politely. Particles can be created, destroyed, absorbed, emitted, and transformed. Paul Dirac's relativistic quantum theory pointed toward antimatter, and the positron's discovery showed that the deeper world contained more possibilities than the older particle picture had allowed. Quantum field theory brought these ideas together. In this framework, particles are not usually treated as the most basic layer of reality. They are excitations of fields that exist throughout space-time. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Quarks are excitations of quark fields. Gluons arise from gluon fields. The Higgs boson is an excitation of the Higgs field. What seems like a tiny object is, in the deeper theory, a measurable disturbance in an underlying field. This does not mean matter is vague or unreal. It means matter is not what it first appears to be. Ordinary objects feel solid because many layers of physics work together. Electron fields, quark fields, electromagnetic interactions, atomic structure, the Pauli exclusion principle, chemical bonding, and thermodynamics combine into stable large-scale patterns. A hand does not pass through a table, not because atoms are tiny hard balls pressed together without space, but because quantum rules and electromagnetic interactions prevent the atoms from easily overlapping into the same states. Solidity is not simple hardness at the bottom. It is organized resistance. The Higgs field adds another layer. Its non-zero value throughout space helps give certain fundamental particles mass. But even here, the answer is not simple. Most of the mass of ordinary matter comes from the energy of the strong interaction inside protons and neutrons, not directly from the Higgs field alone. Reality is not created by one field acting in isolation. It emerges from many fields interacting, shaping one another, and forming stable structures. Even empty space becomes more subtle. The quantum vacuum is not a simple nothingness. It is the lowest energy state of fields. It is not filled with ordinary particles, but it has structure, ground states, zero-point energy, and measurable consequences such as the Casimir effect and the Lamb shift. Apparent emptiness is still part of the field-based description of the universe. At cosmic scales, the story remains just as strange. Quantum fields may have played a role in the early universe, possibly helping seed the large-scale structure seen in galaxies and the cosmic microwave background. Yet the theory is incomplete. Quantum field theory does not yet include a full quantum theory of gravity. General relativity describes space-time itself as dynamic, while quantum field theory usually works within space-time. Dark matter and dark energy also suggest that the known fields and particles are not the whole inventory of reality, so the answer is grounded but mysterious. Quantum fields appear to create much of known reality by providing the structures whose excitations become matter and radiation, whose interactions become forces, and whose patterns become atoms, stars, bodies, light, and the quiet room around you. But they do not yet explain everything. The familiar world is not less real because it is made from fields. It is real in a deeper way. Beneath every surface, every breath, every shadow, and every soft glow of light, reality may be less like a collection of things placed into emptiness and more like a vast pattern of interacting fields, so steady and consistent that it becomes the world you can touch. So, do quantum fields create reality? The calmest answer is that they appear to create much of reality in the scientific sense, not in the sense of magic, imagination, or consciousness summoning the world into being. but in the deeper physical sense that quantum fields underlie particles, forces, light, mass, atomic structure, and many measurable features of the universe. They are not an extra layer painted over reality after the fact. They are part of the best tested description of what reality is doing underneath the surfaces that feel so ordinary. The journey begins with the old picture of matter as solid stuff moving through empty space. That view was powerful, and for many everyday purposes it still works. Newton's mechanics described falling objects, planetary motion, forces, and predictable movement with astonishing success. But then Faraday began thinking in terms of fields, invisible lines of force spreading through space. Maxwell turned electricity and magnetism into one unified electromagnetic theory, showing that light itself was an electromagnetic wave. Already, before quantum physics had fully arrived, empty space was becoming less empty. It could carry fields, waves, influence, and energy. Then classical physics began to show its limits. Planck's quantum idea revealed that energy exchange could come in discrete amounts. Einstein's explanation of the photoelectric effect showed that light could behave as though it arrived in packets, later called photons. Einstein's relativity then reshaped the meaning of space, time, energy, and mass, making it clear that any deep theory of reality had to respect the speed of light and the structure of space-time. De Broglie suggested that matter itself had wave-like properties. Schrödinger and Heisenberg built quantum mechanics, where wave functions, uncertainty, probability, and measurement became central to describing the microscopic world. But quantum mechanics alone was not enough. Dirac's relativistic quantum theory showed that when quantum physics and special relativity were brought together, new possibilities appeared, including antimatter. The discovery of the positron confirmed that this was not just mathematical decoration. Nature could create, destroy, and transform particles. Reality did not behave like a collection of permanent little beads moving forever through a passive void. Quantum field theory gave physics a deeper language. In this framework, particles are excitations of fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Quarks arise from quark fields. Gluons arise from gluon fields. The Higgs boson is an excitation of the Higgs field. Quantum electrodynamics describe the interaction between light and charged particles with extraordinary precision, while quantum chromodynamics explain the strong interaction that binds quarks inside protons and neutrons. The weak interaction revealed how particles can transform, allowing processes such as beta decay and helping the sun shine. The Higgs field added another remarkable layer. Its non-zero value throughout space helps give certain fundamental particles mass. Yet even this story is more subtle than a single field giving weight to everything. Much of the mass of ordinary matter comes from the energy of the strong interaction inside protons and neutrons. The visible world is not heavy simply because tiny pieces have mass. It is heavy because fields are active, energetic, and bound into stable arrangements. The Standard Model gathered many of these ideas into the most successful inventory of known microscopic reality. It includes matter fields, force fields, and the Higgs field, describing an extraordinary range of particles and interactions. It is not perfect, and it is not complete, but it shows that modern science's deepest tested picture of matter is not mainly a list of tiny objects. It is a map of fields and their behavior. Even the vacuum became strange. Empty space is not filled with ordinary particles, but in quantum field theory, it is still the lowest energy state of fields. Vacuum structure, zero-point energy, the Casimir effect, and the Lamb shift all show that apparent nothingness is not the simple absence imagined in everyday life. The stage on which reality appears has its own quiet physical character. At cosmic scales, fields may have shaped the early universe itself. Quantum fluctuations may have been stretched during cosmic inflation, helping seed the structure that later became galaxies and clusters. Yet gravity still remains outside the completed quantum field picture. General relativity describes space-time as dynamic, while quantum field theory has not yet fully absorbed gravity into one final framework. Dark matter and dark energy also remind us that much of the universe is still not understood. There may be fields or field-like phenomena beyond the standard model still waiting to be discovered. So quantum fields do not make the everyday world unreal. They explain why it can be stable, structured, measurable, and richly varied. They help explain why atoms hold together, why light travels, why chemistry works, why stars shine, why matter has weight, and why empty space is not quite nothing. The answer remains incomplete, and that incompleteness matters. A full quantum theory of gravity has not yet been confirmed. The nature of dark matter is unknown. The origin of dark energy remains mysterious. The deepest meaning of the quantum vacuum is still debated. But the direction of modern physics is clear enough to be quietly astonishing. The familiar world seems to arise from fields, interactions, symmetries, and quantum rules beneath ordinary perception. And so the night returns to something simple, a quiet room, a hand resting on a surface, light moving softly through the air. The world feels still, solid, and familiar. Yet beneath that calm surface, quantum fields interact with such consistency that reality holds together, not as a simple collection of things in emptiness, but as a deep and delicate pattern that has learned how to feel like home.